Okay, I think we are starting 3:30. So welcome to this session on data-driven intelligent digital twins, which following a number of sessions previously at EDBF, the one on digital twins on manufacturing earlier today, but also others that I will mention. So if you look into the short description, the slight difference with this session and the others is that we actually look across different domains with reference to the manufacturing domain, but also in building and construction, in the environment, and others, to have presentation of digital presentations or different perspectives from these different domains. So in the agenda, I'll start with a little introduction to the context and motivation for the session. Then we'll hear about digital twins from the manufacturing area, from the ocean, from building and construction, from process industries. Actually, the first will also be on the process industries. We have a set of projects on digital twins for cognitive plants, and also coming into oil and gas at the end, and then discuss as a reference point the asset administration shell for digital twins in manufacturing and how they might relate also to other domains. So that is the setup we have for now. For the structure, let's see, now it suddenly jumped to the last slide here, so I have to go to the right slides so we can continue correctly there. And here we had just before this on Wednesday, I gave a little broader introduction to digital twin pipelines in the transcontinuum, so you might take a look at more details there. As I mentioned, we had this AAS session recently that you also can look at, and just before this on and there was an earlier one on data spaces and city digital twins. So there's a lot of digital twin sessions that you might refer back to. The motivation that I have on this is that from SINTEF, we have a number of different institutes with different domains, from manufacturing to process, building, construction, environment and climate, the marine industry, oil and gas, agri-food, health, and they all talk about digital twins. We work on this from SINTEF Digital in all of these areas, and we see interesting similarities and also some differences that we want to explore. In particular, as it comes to standards and a lot of ongoing initiative for standards that we see. We use now the manufacturing domain, AS, Asset Administration Shell, as a reference point, but we'll also compare this with other approaches as they are looked at from projects, from the IoT perspective, from the AI perspective, from classical manufacturing, from process plants for building and construction, and also smart cities, as well as spatial twins in environmental geospatial context. Looking at these models that we find in all of these standards, which could be a whole seminar in itself, we see there are a lot of commonalities. In BDBA, we have the reference model to the right, and then you say AI, other reference model or overview to the left. And they all have activities or areas related to data acquisition, data preparation, analytics, and visualization that we can also interpret in the context of digital twins. So here is one refinement of those 4 areas into digital twin data acquisition, data representation, digital twin modeling, and visualization and control. So we will occasionally mention these steps as common aspects for different projects. We also have a special issue on cognitive digital twins emerging in MDPI, where we still might have some opening for new papers, but there will also be a collection of interesting papers here. So what we'll do now is to go through a number of projects with different perspectives of digital twins, and then we'll discuss at the end. And we start first now with the cognition for digital twins, also talking about the cognition aspect by Nenad Stojanovic from ISATEC. So then you can take over, Nenad, and I'll stop sharing.
Yes. Sure, good afternoon. Could you just confirm that you can see the slides in the presentation mode?
Yeah, it looks so.
Thank you very much. So I'm Nenad Stojanovic, I'm CEO of Nisatech, and I'm presenting results from the cognitive project. Arne is technical leader, and we are developing the portfolio of, let's say, advanced twins, which are called cognitive twins. And I am now talking about this cognition part, which is still in progress, but the ideas are quite mature, and I'm looking forward to discussing about these results. First of all, motivation. It's about process industry, but actually in all other industries, we can see this nowadays extreme dynamicity, which is introducing problems in predicting the work of those systems. Because if it's a situation very dynamic, then we cannot really think about predicting very seriously the future behavior. The system is continuously changing. And this is introducing a lot of problems because this dynamicity is obviously introducing kind of changes in the infrastructure, and usually it is leading to different types of degradation of the infrastructure, meaning tools we are using. And this is introducing a lot of problems because then you cannot really plan how to use your infrastructure. And the next slide is illustrating this for the steel production. It is toolware, which is obviously manufacturing term, but I'm using here just in order to generalize the notion of the tool or equipment degradation. So one of the partners is the cognitive is Seidner, and we have, as you can see, as you can always probably very hard condition, harsh condition, high dimensional spaces, which are related to how many parameters are considered unknown phenomena, because you are working really in something which is extraordinary environment. And on the right hand side, you see, first of all this data, or let's say the sketch of the data, and at the bottom you see also what is the results after a couple of hours of using some of the equipment. You see that the bricks which are covering the wall are completely destroyed and should be replaced. And this is exactly one of the key problems we have. Not only in this use case, also in other use cases, there is a problem of tool or equipment degradation, which leads us to the very interesting solution, which is hybrid, because we have the data and we can provide different type of the data-driven methods, and we can learn from these methods also prediction models, for example. On the other hand, we have also partners which are very strong in the first principle modeling, numerical modeling, and obviously can develop so-called physical-based models. And on the right-hand side, you see also different type of the hybridization which can be applied. So it is a rather valid approach. But as you see in the title, it's not enough, because the system is very complex and all these are not so imprecise. Data is missing, so we cannot deliver really good data-driven models. And process is unstable. Actually, we are really very blind regarding that what will be happening in the future, because instability is extreme. And this is where we actually talk about cognition, because that's what is actually connecting all these dots, because obviously the Seidner, this process of tool bearing has been or is managed, but it is managed by the human. So if we talk about this, how they are resolving the problem, there is a human in the loop. There is a technical operator who is really taking care about how and when all these tools, I'm now talking in very general terms, but obviously these are the ladles and they have to be refactored after 40 or 80 hits. I'm not going into details of the use case, just to give you the notion of the human in the loop who is really deciding about that, when and how to deal with the tool degradation. And obviously he's using cognition, he's using his knowledge and some other aspects like intuition. And intuition is that what you see on the right-hand side, because he's looking into previous, or let's say past execution of a process. And by looking into this red and yellows, he's getting I'm again repeating this word intuition about, is it okay? Is the process stable? Can we go for the next run, in this case, the hit, or we should stop? And this is this mix of the knowledge and experience, which should be modeled in a way, and which is actually making the problem very, very, very difficult and obviously challenging for the project. I'm now illustrating this, what I was trying to explain. So you have this different type of the different usages, which are called hits. And then each of those, there are some kind of parameters which are observed. Some of those are reported to the user, and the user is doing visual inspection. So you can see on the right-hand side, he's looking into, after several hits, okay, let's say 40, is looking into the walls, and then he's also looking into he's looking into this after having decided to do the replacement, just to be correct. But he's looking into these reports, which are actually reflecting somehow the state of the ladle, and then he's making a decision. Then he's writing the report, and then it can be validated. What we have developed is a cognition concept, which is, as you can see here on the right-hand side, sitting on top of the digital twin and hybrid twin, which are not the topic of this presentation, so I'm really skipping this. But just imagine that we have also some background for or preparation for this cognition, which is then taking into account human knowledge. You see documented knowledge or human implicit knowledge, and then trying to understand how this knowledge really can be combined with other information in order to make the right decision. And this is how we are realizing. It is realized using some orchestration tool. In this case, it's a stream pipes, and you have different pipelines for different types of modeling. One pipeline for the data-driven, in this very case, data-driven model, and another for the hybrid, for the numerical-driven model. And this is hybridization, as I illustrate now on the screen. So these two are combined, and then on top of that, we are putting also the cognition or expert knowledge in order to do and to realize the cognition. So the main intuition here is that the expert knowledge should sit on the different other types of the knowledge and do the combination as it will be done in the reality. So by using different association, or I'm repeating for the third time, intuitions, in order to understand what is really going on. And this knowledge is modeled by using technology, in this very case, by using technology which is called complex event processing, because this is the possibility to develop declarative statements about how some of the events can be combined. For example, we tried to interview him and to see what he's really doing. And the main point is that he looking into unusualities in that what is happening in the measurement. So this unusuality in how red and the yellow are distributed is actually making the job. In this very case, we cannot obviously, by using CV patterns, we cannot do the unusuality detection, but we are doing this now with other technologies, especially by using neural networks. But in this very case, what we have already done is CV patterns, which are looking into anomalies which are happening in the last time. So by understanding that in the last n hits, there was a lot of anomalies, very likely indicate that the next hit should be avoided and the ladle should go to the reparation. There are also different types of other patterns. I'm now skipping them because this presentation is really about introducing you the notion of the cognition and how it's implemented in the cognitive. And then obviously the infrastructure we are using for implementing digital twin architecture or digital twins is based on some standards. In this case, it's AAS standard model. I'm not repeating this slide because probably many of you were listening to the previous session where Ilyana was explaining this as a part of her presentation. I'm just announcing, or let's say summarizing. On the left-hand side, you have your assets, and then in the middle is a digital twin, which is actually outsourcing the business logic in these Apache stream pipes I already presented. So digital twin is using the models which we are developing in the Apache stream pipes or this orchestration in order to understand what is going on and to test, to simulate. And there is a user who is administrating or managing those models, and the user who is also using this final technical operator who is using digital twin in order to get the recommendation. In this very case, obviously, we are just giving recommendations. We are not saying to him, okay, you now have to cut, to change or whatever, because the human is really in the loop. And this is one of the questions we have in the previous panel about the role of the humans. Probably we can have it in this panel as well. So the role of the human, even if you have this cognition and everything is perfect, there is a human in the loop. And this is the last slide summarizing actually what I was trying to explain. And this is that the cognition is sitting, first of all, on the data-driven, as you can see on the left-hand side, on the data-driven and model-driven approaches. And then it is introducing top-down expert knowledge. And this is how the cognition is realized. And then this cognition enables us to combine all these models. So data-driven services and model-driven services combined with the knowledge expert intuition in order to interplay all of them. We are using stream pipes as a good tool for doing this kind of orchestration. Also other tools should be used, but in the essence of everything is kind of an assembly of all these methods, which are then leading to the proper decision-making process. And this is actually finishing my presentation. Thanks for your attention. I'm open for the questions now or later on. Thank you very much.
Yeah, thank you. So please put your questions into the chat so we can deal with those towards the end, so we can run through all of the presentations now. Thank you, Nenad. We'll continue now to a different domain, namely our environment, the planet, destination Earth, and digital twin of the ocean, and the project Iliad by Georgios Silias from Democritus University of Thrace. So please, Georgios.
Thank you, Arne, and thank you for inviting me to take part in this session, very interesting session. As you said, I will introduce you to Iliad. Iliad is a project that hasn't started.
So now we see also your slides to the left, if you switch for the presentation mode.
Sorry, I am in the presentation mode. Hold on a second.
So maybe you can switch between the two screens. If not, I mean, it's okay. We see what you see, but we also see your slides to the left on the slide on the screen.
Sorry, hold on a second. I will share again my screen, and I hope you can see now.
No, it's
okay.
Yeah, perfect. Thanks.
Okay, thank you very much. And I was saying that now we will move to the oceanic environment, and this is the project Iliad. It's funded by Horizon 2020. It's a project that hasn't started yet. It's a project that will start on the 1st of February. And the coordinator is Intrasoft, a multinational company, and the consortium is comprised of 56 partners. The total budget is 18 million euros, and the duration of the project is 36 months. So we are now in the preparatory phase. I would say that Iliad project was our response of a consortium in the call of the EU Green Deal with this code number, and the name of the call was referring to the transparent and accessible seas and oceans towards a digital twin of the ocean. So this digital twin falls within the overall scope of the EU to develop a digital twin of the Earth, and this is the Destination Earth initiative and the mission of the Destination Earth. So the final goal of the European Union is to develop a system that will be able to simulate with high precision the atmosphere, the oceans, the ice and the land areas, and to provide high resolution, highly accurate forecasts on extreme events like floods, like droughts, like unforeseen events like fires, on different time scales ranging from years to days. So this is the ultimate scope of Iliad, is really to contribute to this Destination Earth initiative, and this is the context of the digital twin of the ocean as we see it in Iliad. So we try to integrate existing assets, existing infrastructure that has been developed already in the European Union by integrating databases, infrastructures that are on a daily scale run operational models, or physical ocean observatories with deployed sensors operating in the sea, with the digital environment, the digital technologies, the cloud, the supercomputer capacities, the AI and the data analytics into one unified digital component. And all this will, of course, create a consistent, high-resolution, multidimensional real or near real-time description of the ocean. And as you can see here, the concept is really to the left-hand side, you see the various infrastructure that we consider as important for this project, like Copernicus, IMODNet, all the other DIAS infrastructure that exists, like SeaDataNet, and the data that are coming from the different observatories, the regional or the local observatories, with the sensors deployed in the sea. And then we have the interoperable space of data sets and services. And this will be merged with hybrid models, models which are deterministic or models which are run in the AI mode. And they will give us customized dashboards to provide services to the various end users. And I will show this to explain exactly what I mean. To the left-hand side, we have the various data that come from sensors, the sensing tools. We have remote sensing, the satellites collecting data on a daily basis. Then we have in situ sensing, and then we have what is the modern approach, the social sensing, that again has a significant value. And we should integrate all this into one hypercomputer, where we can create and organize all this data into data cubes, or run simulations, or develop statistical and probabilistic products, or use machine learning, image processing, or rule-based modeling in order to be able, for each specific location, for each specific time, to describe the conditions of the sea, and also to provide alarms and to develop a series of information for the end users. And who the end users, what sort of applications we have in Iliad. We have considered that this DTO will be able to provide information to the policymakers, to the working in the ecosystem environment, then to the shipping industry, the ports, the marine renewables, people working in fisheries, the oil and gas sector, and the aquaculture. So this is more or less the context of the project, and we follow a 5-dimensional approach. So we have one hand the dimension of time, the 3D space dimension, and then is the test case dimension, because we focus in specific pilots, and we consider each pilot a specific DTO. So we have the marine renewables pilots, the existing wind and wave energy farms, the ocean energy, the OTEX, metocean hint casting, now casting and forecasting DTOs, the coastal sediment transport issue for harbors, the aquaculture, the fisheries, and the monitoring of ballast water, the monitoring of and the forecasting of jellyfish, the safety of harbors, the microplastic pollution, oil spills, and the issues related to extreme events and insurance. This is the spatial distribution of 4 our pilots, and as you can see, we cover areas so in the Black Sea, in the Mediterranean, in the open Atlantic, in the North Sea and the Baltic. So we cover all European seas with a cross-sectional, a variety of cross-sectional different services and different DTOs we develop. And these are the summary elements of the Iliad DTO. I would say that the system is expected to be able to interact with existing data platforms, so to act as a twin of the twins. We consider the user engagement as a significant context of our system, so that the users interact with the system and give us advice on how to proceed with its designing and development. The DTO will be operational and will perform in real time, and will cover a variety of space scales from coast to very fine, and will also streamline data from the ocean and the fresh water, the rivers. We collect data using low-cost sensors, because we need to cover and to monitor different parameters. We will introduce in the ocean the low cost and the cost effectiveness of monitoring. We will try to develop, upgrade, and integrate novel sensors on existing vehicles like drones or microplastic sensors, or the concept of eDNA. We'll utilize the IoT technologies, the harmonization and standardization of data to a central cloud system, the simulation of all this data in simulations, and the advancement of thematic models, the employment of machine learning and AI on advanced data technologies, and the overall extraction of patterns and trends from the hidden, which are hidden in the data. Of course, we wish really to be able at the end of this project to issue warnings and alerts at operational scale to a variety of users. And for this purpose, we are linked
So you have 1 more minute, Georges.
Yes, I'm about to end. To aid the EU policy instruments implementation, the policy impact facility, and we develop a business orientation, this DTO, with the Iliad marketplace. This is one of the platforms which will be used for the development of the Iliad. It's called Marinomica. It's a system that describes the conditions in the sea in the Mediterranean currently, but it will expand to the other areas. And as you can see, the Iliad DTO will be also integrated within the Gaia-X reference architecture. And this is it gives you an idea of the different work packages that we will work within this project from February, starting from 1st of February. And this is the structure of these work packages and the interrelation and how these work packages really lead us to the development of this DTO. Thank you very much.
Thank you, Georges.
Thank you.
So we are now switching again to another domain, namely building and construction, and the project BIMprove by Gabor Ciebic from Center for Manufacturing. So please go ahead, Gabor.
Yeah, I hope you are seeing my screen. Can you confirm it, please?
Yes, we see it.
Yes. So then let me thank you first of all for the possibility to present the project here for you. So it's a project about the construction sector. We would like to improve the building information modeling by different real-time tracing of the construction processes. We are in almost past the 1-year milestone for the project. So here you will be seeing results so far. And then the very first part, so the idea is that we, of course, why are we here? These are the reason are the digital twins. So the digital twin, in our kind of interpretation, it will be a dynamic version of the static building information modeling kind of environment. So this is what we would like to kind of achieve, that we actually expand the today's standards with new possibilities that are related to the building information modeling. And how we achieve it, it's while we create a kind of recording of all the things that are happening on the construction site, so on the itself site, so creating like we can call it like a YouTube of the construction site. So we gather all the information available on the site, store it, analyze it, and then provide services based on that. We have a consortium from 12 partners, as you can see, 5 countries, really widespread of the consortium. And our main kind of idea is that the twin itself, it needs to be kind of inputted with data and data flow from the sources existing. So like survey data from the construction site, from historical data, from the model itself, and also time-related information. And based on that, we create a digital twin that provides analysis services in related to safety, in related to cost aspect, and also to time aspect. And how we communicate back all the information to the users, that is also part of this project. These are that we create user interfaces and also hardware for the users that can feed back the information, like, for example, onboarding it into a truck, for example, a tablet-based system, and also something we refer to as a site office, where the site manager can actually virtually explore the digital twin while still sitting in its own offices. We have constructed this kind of digital twin in BIMprove in a kind of layer service architecture. We also published a white paper on it, and you will be also having access to that at the end of my presentation. So we kind of layer-wise, we expand the possibilities of the static building information modeling, as you can see it here on the base, and expand this with the different services and also additional information that are available from the different sensors and also from the robots, for example. What is important to mention here that our solution is only focusing on one part of the life cycle of the building asset, that is only the construction phase. But whatever we are developing throughout the project, it will be available also for expanding to, for example, operation or innovation phase, so like covering the whole life cycle. But today we are only focusing on the construction phase. How we think that these layers are working and how partly we are already implemented it. So we have these, all in all, we have these 6 layers. The BIM layer is the static one, and the rest are either services provided by layers or are digital twin related services. So we say that we group these layers into 2 main categories. One is that is kind of information containment about the geometry and the documentation of the building asset itself. And then we have those that are actually modifying this underlying geometry and documentation. So like the analytics, safety, cost calculation and shadowing. So how we see that also all the information that we interact with the users are actually connected to the so-called digital twin layer, and the rest of the information is kind of hidden from the user. So it provides as a service to the user. So interaction and kind of reading of the information is directly to the static building information modeling, and the interaction around that. So how we kind of access it has to be done through well and predefined interfaces, which we already published in our Zenodo repository, that how it can be done. And then all the kind of the calculation results, so how the things are progressing, what will be the cost of the changes and what's the next step, those are notified to the user for kind of discussion and decision making. And in order to hide kind of sensitive information. So for example, construction companies and general entrepreneurs are very much interested on protecting their information related to, for example, cost calculation or time calculations, those that we are able to actually hide it in the different services of the layers and only provide aggregated data. So we are not kind of revealing any company secret to any of the people who is using this digital twin later on. And what is important to mention here, that the analytics layers is responsible for creating as-if scenarios. So whether what happens if this is delayed, what happens when the other things are not built correctly, and so on. So this is very important, that the analytics will provide you with the necessary information of the as-if or these kind of decision points of what is happening. Yes, and how we kind of interpret this to the information, it is that we are making a kind of, in software world, we call it like a repository information, like we are kind of progressing. We are progressing one by one day. So at the very beginning of the construction site, we are having the first kind of a day where we know that where is today's status, and then whatever changes are happening on the kind of the geometry or at the construction site, we are able to save and store this information day by day and trace back where the changes happened. So it is a kind of a traceable and provable at the end of when the construction actually finishes. We are able to actually follow back that whatever changes has been done, these are traceable back, which makes also possible that the BIM model will be, in the longer term, be a contract-based solution. So we are working toward that the BIM model would be a contractual information and not as a byproduct from the construction site. And for those who are not familiar with the building information modeling itself, so we are based on IFC, the Industry Foundation classes. These are standards per today. Latest edition is the 4.1, that is the official version of it from 2018. It has a tree structure, so it's very much adapted to this kind of alternation check like digital twin-based workflow. So it is a good traceable. Changes can be really easily traced back that where did happen, and we see that with a proper software solution, we are able to actually use this information further on. So if you see now in details that how this is kind of executed, like in general, IFC is built up from geometrical information and also something that's called properties. These properties per today are, in most of the cases, are custom-based properties. And in our case, we would like also to introduce a new property, which creates this kind of follow-up or kind of change revision possibility in the itself, the digital twin itself. What if we look into details in the standard itself, so what we see, what's included for today, these are the geometric quantities and stored with a unique ID. And what we do is we expand this information with the timeline. So we create a kind of a rolling window of what is happening on the construction site, and we expand this information with the tasks. For example, building of a wall. We also expand it with, for example, the robotics or drone-based inspection. And all of these are stored in this something we call dynamic building information model. And that was from my side. Thank you very much for listening to me. And if you're interested, you can read more about the project either in the white paper or on the homepage of the project. Thank you very much.
Thank you, Gabor. There is one question here that you might answer quickly. Can you provide climate adaptation strategies? And if so, how?
You mean that if the climate has any kind of an effect on the construction site, and based on that rescheduling, for example, a construction process?
Or things like zero emission buildings, I would assume, or looking at the relationship to the environment.
Yes, it's the digital twin allows us to actually these kind of calculations that we can refer to like LCA calculations. These are included in the kind of the also in the design phase of the building and also in the construction phase of the building. So we are actually able to include that measurement information. So for example, the concrete, like the setting of the concrete, how many CO2 was emitted. These are information we could actually gather and store when the construction is finished, and we can actually provide this information to those who are using in the operation phase of the building asset.
Thank you, Gabor.
Yes, thank you.
Switch again back to the process industries. We will have two presentations following now on the Factlog project first, and then Cogniplant. These are two of the 6 projects that are all active in cognitive plants under Spire. We heard about Cognitive before and Capri in the last session. And now we will hear about Factlog from Kostas Kalaboukas from Magioli. So please, Kostas.
Thank you, Arne. Share my screen. I'm sorry. Can you see it now?
Yeah, it's in presentation mode.
Okay.
Well, we see actually your notes or slides to the left. So no, it's fine.
It's okay.
Yeah.
Okay. So
thank you.
Thank you for the invitation. Thank you for giving me the opportunity to present Factlog project. So I will speak about the application of cognitive digital twins, a concept that already mentioned before by Nena and the other speakers, and how we have addressed this in the process industry with some examples of the scenario of the pilot cases. So I think I will not stick too much in this slide because already was mentioned. So we have identified the 7 key enablers of how digital twins can operate in a cognition mode. So we have first the profile, which is represented by the knowledge graphs, 3D model specifications of the process, which can be done either at the asset level or even at the process, depending on the granularity the factory wants to monitor. We have the cognition part, where it incorporates all the analytics models and the cognition parts. We have the life cycle, which represents how different, what is the life cycle in terms of duration, how you are creating, how you are designing the digital twin, how you are monitoring, and what happens after the end of the uses of this digital twin. We can have also static digital twins or ad hoc ones in response to different ad hoc events. We have the computation issue that has to do with whether you want to monitor cognition at the edge, fog or cloud. We have the communication part, which is very important. The idea is that you can have either a digital twin for a particular asset, or you can have a network of digital twins, each one interacting with each other, thus constituting a more abstract level, like a process or even at the factory flow. And we have, of course, visualizations and trustworthiness with regards to the data models and the information that has the analytics models and all the security privacy aspects that have to be modeled and enforced as policies. Now, given these enablers, our vision for cognitive process industry is that a process can be represented as a dynamic living system of digital twins, which can represent other the assets, operations, and actors involved. So we can have different granularities of digital twins, either at the shop floor level or the process and even the plant level. And of course, we can either also monitor the whole supply chain as a network of interconnected factory digital twins. We have seen that there are cases which require different level of cognition, from basic understanding to autonomous decision-making and actuation. That depends on the customer and the process needs and each of the operation particularities. And of course, we have to align local cognition, edge cognition, and the global cognition at all levels. Now, based on these enablers, in Factlog, we have identified the operational model where we start from the modeling of the factory or of the industry or the supply chain as a network of digital twins, and we try to specify what is the behavior model for each digital twin, what kind of decision each digital twin is about to make, and what is the level of cognition they have to do conceptually. Then we identified the data streams from operations, external data or sensors, and this creates a new knowledge which have to be understood, have to be used by the analytic services in order to map new knowledge into the existing behavior model. And then we have simulation and prediction. That means in the case of anomaly, to understand what would be the impact of this anomaly, or to propagate the behavior of the process into the future, given the existing behavior that we have already identified. And then we have the optimization part, which are decisions based on the anomalies, which can be done either a response to an event, or to make a new process scheduling, or to make a new predicted maintenance plan. And this decisions optimization has a loop back to the simulation prediction, in the sense that how my optimization scenario will produce the results by making use of the simulation prediction services. So I need to understand to validate my optimization solution. And then we have the actuation, which can be done either automatically or with the human intervention. The architecture is based on So I think, so we have the architecture, which is on the right side, we have the digital twins platforms responsible for collecting data from different information sources through a message and service bus. And you have the analytics service here, which can be either variation detection, anomaly detection, create generative models, those services that we have identified in Factlog, but in general, it is scalable. We can orchestrate different other services. And we have the optimization, which is a part of the whole decision-making process. And on the left side, we have the knowledge graph, which provides the necessary representations, and the process and the simulation tool, we call it PSM tool, which is in the case of process industry, process models are very important, and they are used in order to simulate the behavior of the system. And we have different visualizations and pilot-specific tools, which represent the different needs and the cases that we are addressing. I just want to show you one indicative scenario, which is very, very interesting. So this is the case of a refinery scenario from Tüpraş partner. Tüpraş is the biggest refinery in Turkey. So the idea is they have the LPG production is here, and the LPG production is the result of 10 different processes which run in parallel. Each process has its own different, let's say, conditions of process. So the idea is that we have in each process unit, we have sensors, we have data coming from either real time or from periodic from various lab tests, and we have some event detection services in order to identify potential anomalies. Now, the interesting point here is, and this is the differentiation of a process industry. When there is, they want to test the percentage of two main ingredients, C2 and C5, and they don't want to have these ingredients to be measured here, because when they see an increased here, they cannot do anything because it's the end of the process. So they need to identify as early as possible in the process where is the problem. And I imagine that they find here with some event detection services that there is a potential problem that, and I know that the C2 percentage is increasing. So this means that I can make a impact assessment and simulation that the C2 percentage will be high here. And the problem is that how I can identify the optimal phase in which to interfere, because it's a process industry. We cannot stop the process in the refinery and say, okay, I will examine here, but it's a continuous flow. And the idea, we use optimization in the analytic services in order to identify the best intervention points, and then based on these points to understand which will be the ingredients that need to be put inside, so that continually and gradually the LPG constitution will be normal here. So this is a very interesting case and shows the dynamics of the process industry. And how we have tackled this problem is first we modeled all the process units as autonomous, as individual digital twins, and then we modeled each of the 10 processes as a process digital twin, and then we have we are using analytic services for event detection, prediction, and simulation, and for each of the process digital twin, and then we do the optimization at the process level.
One more minute, Kostas.
I will finish in the last slide. And other scenarios that we saw in this project, we have in the process industry, we have energy monitoring, and I put in parentheses, not just energy, could be water or other resources, it could be soil, depending on the industry. And we know that the process industry, the energy is really high critical factor. We have the case of optimized asset operations. The idea is that a machine, knowing its production schedule, can continue running or continue operating or be on a safe mode or stop, and then it makes sense that we open again, switch on again the machine, because that has to do with the energy spent during the operation. We have predictive maintenance and optimized production scheduling, not just considering the orders and time and cost factors, but incorporating the resource usages in the whole optimization algorithm and model. So these are the insights from Factlog project, and thank you for the opportunity to present it.
Thank you, Kostas. We continue in the Spire process industry sector with the CogniPlant project by Stefano Elero from Stantec. So you can stop sharing, Kostas, and then Stefano can start his presentation. Still see your screen now, that's fine. And then,
okay, can you see my screen, Arne?
Not yet.
Okay, let me try again to share it.
There you are. Okay, very good. We see it. Thank you.
Better. Excellent. So thank you very much. Thanks for giving me also the opportunity to introduce to you the CogniPlant project. It's a pleasure to be here. So the idea of the CogniPlant project was born in response to the challenges that the European process industries are facing, and we basically saw most of, let's say, this burden in the previous presentations. I'm talking about the shortage in raw materials, the increased cost of energy, the environmental constraints, of course. So we realized that there is a large room for improvement in the digitalization process, but often this, let's say, potential is kind of unexploited, especially in terms of data sources. And basically, we could use that potential to improve the performance and the efficiency of production plants through a number of technologies to be deployed. So our ambition is to demonstrate an approach for the advanced digitalization and intelligent management of the process industries. And to do so, we will develop a novel vision to data monitoring and analysis that will use, let's say, the most recent developments on analytics and cognitive reasoning, coupled with a disruptive use of the concept of digital twins, which is, of course, let's say, the main topic of the discussion of these days. The requested funding for this project is in the order of about 7 million euros for a 3.5 years project. And CogniPlant is focusing on the process industries that show the highest energy consumption. It's basically the main field of our intervention. In fact, the consortium is composed by 14 partners, and we have 4 end users, starting in Italy with Grigolin, that is a quicklime manufacturer. We have Hermes in Austria that makes abrasive on surface. Ognisol Mina in Ireland is an aluminium refinery in County Limerick. And ACVA is a manufacturer of stainless steel pipes in Spain. So on board of the consortium, we have, of course, ICT experts such as Ibermatica, that is the coordinator of the project, Ingeteam, Savvi, Misterneck, and Logticker. And we have also 3 research and technology organizations that are involved in the digitalization and data analytics, namely IDECO, the Technical University of München, and the Software Competence Centers of Hagenberg. And finally, there are 2 experts on board on exploitation and communication activities that are respectively core innovation and STAM. So this is basically a schematic of our view of the CogniPlant approach. The solution will provide a hierarchical monitoring and supervisory control that will give the operators a comprehensive vision of the plant's production performance, as well as the energy and resource consumption. So, as we see, the approach is structured in 3 layers. The first one being the sensing and data virtualization layer, which is collecting and structuring the data from sensors and the production equipment. The second layer is the data analytics one, where data mining, data processing, and big data analytics occur together with machine learning techniques for this, let's say, endeavor. And the idea is to use data analytics to extract the valuable information from the data that we have collected, and information concerning both the process and their effect on the overall performance of the production plant. The last layer is the co-decide model and the simulation model. So this is where we have the digital twin, the decision-making tool, and the generation of the operational plans. Thanks to the digital twin models, we can design and simulate the operational plans that are somehow optimizing and improving, in last point, the performance of the cognitive production plans. So as far as the outcomes of our project are concerned, especially for the industry, for the users, well, the public and open access outputs will be the public deliverables, which are part of our dissemination material, but Cogniplant, of course, will also produce exploitable results, including hardware and software tools that can be beneficial to improve the performance of plants, to increase the productivity and reduce the emissions. So these results will be made available as products and services by the various partners who developed them after the end of the project. And there is, of course, a part of activity that is devoted to the business planning of this part of the results. So this is just an introduction to the project, and I will be glad to answer your questions that you would like to drop in the chat. Thanks very much for this.
Yeah, thank you, Stefano. We'll get back to this perhaps also in the discussions, as we see there are different approaches on how to capture and manage data. I think we'll continue now with the last of the presentations here on IFM, Information Management for Digital Twin Assets, by David Cameron from the University of Oslo and the SIRIUS Center. So please, David.
As well, and try to share screen.
You might need to unshare your screen, Stefano. Yeah, fine. There we are.
There we go.
Thank you.
And then I can put it into the full screen mode, please. And then I think I have to go swap it in slideshow. Okay, so you should be able to see a full slide here.
Perfect, thank you.
My name is David Cameron. I work at the University of Oslo in a role at something called the SIRIUS Centre for Scalable Data Access, and also at the newly created University of Oslo Centre for Computational and Data Science. So what I'll be talking about is something a little bit off from what the other projects have been, in that this project is not a European project. It's financed by oil company money and Norwegian research money. But it'll be about an information modeling framework and how it relates to digital twins. I represent the SIRIUS Centre for Research-Driven Innovation, which is a Norwegian research centre built to try to mobilise IT for the oil and gas industry. And we've now grown up to 20 partners. We've got about 1.5 years left in the life of the centre. But as you see, we've got a combination of engineering companies, IT service companies, software companies, and a group of universities led by the University of Oslo, but with the Norwegian Technical University, SINTEF, and University of Oxford. There are many, many complex models of digital twins. Here's an example, and I suspect we've seen quite a lot of these at the conference. When I'm teaching digital twins, I try to use a simpler model, which I call the three-legged stool model. And what we're saying is that you need three things to make a digital twin work. You need a description of what a system's design and configuration is. You need to tie together it with simulation and analysis, and you need to tie it together with measurements and observations. To get all that data together, you then need analysis, reasoning, and decision support, which is AI, or what is now called cognitive. And the whole point is to give a user who's got some role and interest decisions based on the best estimate of what that system state is. Now, what we were looking at today is primarily around how do you get access to the system's design and configuration, although that implicitly defines how you also define and contextualize your measurements and observations and your simulations. So our people who are trying to build digital twins are successfully building digital twins. They can go buy a digital twin of their facility from a company like Kongsberg Oil and Gas, Kongsberg Digital, or one of the big instrumentation vendors. But what they're doing is they're trying to put it into a context of a large capital project. And the information you use to build your digital twin is refined and developed through a project where you take the requirements for what you're going to build, create a design basis, then you use that to build and commission a plant. And when you're built, you'll then have your digital twin and your plant. The challenge is that that information is handed over by paper, in these days, digital paper usually. And that means that you're losing all information that could be being used for cognitive purposes in digital twin because longer life cycle. Every project is executed by what's called a stage gate system, and you then have information which is lost at every handover of data in that information until you get into your operational phase. And it causes a loss of knowledge of why the plant is as it is. And that's the sort of information you want to use for a digital twin. So this diagram is a bit busy, but what it shows is, how you build a large, complex capital facility: chemical plant, oil platform, offshore wind farm, long rail tunnel. You start off with your process from there, and you move from your system concept to your system design, and then at some point you actually get the real life physical system. Now, what you're building up through that is that you're building up what we can call a digital system model. And that's actually what some people call the digital twin. That's sort of what I call the bag of data digital twin. But if a digital twin is actually about analyzing, interacting, and simulating together operational data, you really have your digital twin up as sort of a subset of your digital system model. And would say that the digital twin is what makes your digital system model live. The trouble with that digital system model is it's spread across 50, 60 databases, and it requires information transfer along a long supply chain. So how can we structure that data and make that data better? Well, the petroleum and process industries have been working for decades with describing this engineering data and enabling digital twins. They started off back in the 80s with ISO 10303, and then turned into a standard called ISO 15926. And they're sort of standards for reference data for engineering databases. How do you sort out the data you have about some sort of plant? The oil and gas industry has built on that, and as they've gone into digitalization, there are oil and gas initiatives, CHIFOS, which is about handing over information in a structured way. The German industries are looking at data exchange through a DEXB initiative and the broader process Netzwerke VDI initiative. Platform Industry 4.0 is also involved in this work, and NUMBU is involved in this work. And they're giving us industry-specific models of equipment automation and other things. The Norwegian industry brought together a project called READY, which is looking at how do you represent requirements digitally, and how do you actually link those requirements to a digital twin of a facility or a design, and created this information modeling framework, which I'll present to you. Now, I would make the following statement, that we have okay models, and I'd say only okay models, for representing installed equipment and as built with a tag structure. You know, the thing you go in and say, I've got an as-built plant, I want to build a digital twin, oh look, there's all this tag data, I'll use OPC to structure it. So it's ISO 15926, CHIFOS, DEXB, OPC, UA. What we lack is models that allow us to approach our digital twins with systems thinking, top-down design, and what we call aspect-oriented digital twins. And that's what this information modeling framework is supposed to do for us. Now, the IMF allows us to apply system engineering principles to our information and to our digital twin. It's based on an ISO standard, 81346, which is about system breakdowns, and it's about breaking down complex systems into subsystems along aspect trees. And I'll come back to what that is in the next slide. And those systems and subsystems are typed using an agreed reference designation system. Now, we've developed an RDS for oil and gas. We believe that that is easily extendable to the process industry, energy industries, and should be, because the oil and gas industry is a very, once you get into processing, is a very simple subset of the process industries. The important thing about it is it separates function from the physical object that you're trying to twin product, and allows us easier access to why questions about our digital twin. And it allows you to easily abstract out relevant information from the twin. But it also integrates the old tag-based and product-based support in what's called the product aspect. So what does this mean for some piece of equipment? We approach our modeling through aspects. In common day language and in tagging, we mix all these aspects together when we describe something. But you need to keep them apart because they've got very different relationships. And so what we do when we build a model of our facility, we organize information into information about functions, information about products or components, and information about locations. And then you're free to define other secondary aspects around building your information model and how you structure your information model. So what you do is that in an ISO 15926 or usual digital twins asset model, you're starting by building up around the products. A pump, electric motor, that can be grouped together into a pump system. Those are things that are actually designed by considering a series of functional blocks which don't quite correspond to the pump, but define the actual functionality you require from that equipment. And so the IMF enables you to say, I'm going to build a tree of functions which are then fulfilled by a smaller tree and a more localized tree of components linked together. And then I can also say where they are, what deck I'm on, which room I'm in, which enclosure I'm in. And so the IMF gives you an agreed set of functional systems and breakdown structures, which when you apply it over a digital twin, gives you a much better and finer access to actually why things are built as they are and why they're not functioning as they should be. So this is being worked out in a couple of projects. A project which recently was finished, and all of these projects are done without European support, but on the basis that the industry itself believes that these things are important enough to invest money themselves into the work. So the Digital Design Basis project was a proof of concept saying, can we actually use these principles to create a digital model for the very early description or design of a project? And we brought together 2 oil companies, 3 engineering companies, and a software company, which is part of Arca Solutions, to do exactly that. And we created a data model. We demonstrated that you could take that model, implement it in any relevant software tools you had, and we were able to exchange information in a sensible way between the 2 engineering companies, the 2 oil companies and the engineering companies. That's moved on to a project which is now underway, where there is a fairly large development project in the North Sea at the moment, where Equinor and Aker BP are building a set of oil platforms which are linked together. The Aker BP project is being supplied by Arca Solutions. The Equinor project is being supplied by IBEL. These 2 oil companies and 2 engineering companies now working together to validate and develop the IMF and show that it works to support digital twins and support and digitalize information flow you need to build digital twins in a complex field development. So this is very exciting because we have really high value real data to work with, and we've also got a project that is asking us to deliver things into that. But we need to collaborate and standardize and bring it out into the European landscape. So thank you for that, and that's the contact details if you want to talk to us.
Thank you, David, and thank you all. We heard now 6 different perspectives into digital twins with commonalities, but also on differences. This is what we want to reflect upon. Maybe before we start a discussion of that, we had a previous question on how to provide climate adaptation strategy, which actually was not for the building and construction industry, but rather for digital twin of the ocean with Georgios. It's interesting that climate adaptation is something that impacts probably all of these projects and activities and domains from the different perspectives. Of course, process industry is very energy heavy and also relate to climate. But Georgios might also say a few words about how climate relates to digital twin of the ocean.
Yes, thank you, Arne. Yeah, it's correct that climate adaptation strategy is extremely important for potential investors and investments in the marine and maritime sectors. I think that the digital twin is the tool. The tool is not able to develop strategies. What is going to do the digital twin of the ocean is going to improve the existing climate adaptation strategies that we have, because for the moment we have a series of climate change models that develop a series of scenarios on how the climate will change according to the energy mix that we will follow in the next 100 years. These models are run independently from the other models that describe the oceanic or the water quality conditions, and I think that since all the data, the historical data, the nowcasts and the forecasts in short term and long term will be integrated in a single system, then we'll be able really to interrelate all this data and understand better the long-term future perspectives, and this will help us to develop a better climate adaptation strategy for different locations, for different users, for different marine and maritime sectors. And I think that this will give us a very good perspective of what will happen. While on the other hand, if we take the data sets that we produce and we feed into the digital twin, we'll be able to see which of the scenarios of the climate change is the most appropriate, because for the moment we rely really on pure, we don't have a clear view which is the most appropriate scenario to follow.
Yeah, thank you, Georgios. I then think we move into the discussion part of this session. I think if all presenters turn on their cameras, and also Sergio, who was involved in the previous session on manufacturing and the asset administration shell. Maybe we can start with Sergio saying a few words about, say, the relationship to this session from the previous session on manufacturing, and to what extent the AAS approach to digital twin seems feasible in these various projects that have been presented for manufacturing. And we can also discuss the other approaches and the relationships following that.
Yes, thank you, Arne. So this is Sergio Gusmeroli, Politecnico Milano. I'm co-chairing the Smart Manufacturing Industry Group in BDVA. And I was co-chairing also the manufacturing track here in this event. And in the manufacturing track, we discussed several things, both in the main session and in the digital twin session, which was just before this session. And basically, what we can bring here as a lesson learned is that many people call it Industry 5.0, and so a new revolution for industry. In reality, there are three things: human centricity, resilience, and sustainability. And I've seen that we discussed how digital twins could enable both human centricity, resilience, and sustainability. Regarding human centricity, we discussed how to build digital personas. That is digital images of humans and how humans could interact with machines. There is a paradigm which is called collaborative intelligence from the Harvard Business Review, which says that there are phases where humans assist machines and vice versa. Another point was sustainability. And I believe that also all the presentations here from the process industry, from the maritime industry, from the building, from the construction industry, they are focusing mostly on sustainability, energy saving, waste reduction, and all this stuff. I really wish to pose a question about resilience, because, and it is also what David Cameron said in his last intervention. So, how easy is to make these models evolve according to different conditions, external conditions coming from the market, but coming also from the environment? So how maintainable are these models, and shall we have an estimation of how much time and how much effort it took to get to some concrete results regarding digital twins? And so shall we focus more maybe on the design and engineering, on co-design and co-engineering phase for digital twins? And I believe that this is something that it is common to all the sectors and to all the domains. What I feel is specific is maybe the readiness and the maturity of the market. And in this case, I believe that we could take a difference between large enterprises, SMEs, and between locations and between industrial sectors. And so the point is the adoption of these digital twins, how are they requiring the modification of the processes of the company, of the organization, of the skills, rather than just on the ICT platform and data and software. And so these are the two considerations. On the one side, common is the need of maintainability and evolutionary behavior of these models in order to meet the resilience requirement. And second is how these industries are ready to fully adopt the benefits of digital twins, and in which direction should we go in order to make them more ready and more mature.
Thank you, Sergio. I think these are important perspectives emerging. We heard also from Cognitwin about human centricity with knowledge from workers. We had questions on sustainability and resilience. But we also heard from the different projects that they have taken different approaches to digital twin representations. In the previous session, it was much around AAS, the Asset Administration Shell from Industry 4.0, which indeed is used by many manufacturing projects and also some of the process industry projects. But we also heard about other approaches like knowledge graph representation, like geospatial models, like the BIM, Building Information Models, and IFC, the Industry Foundation classes, the ISO 181-346 and ISO 15926 that David talked about. So there is indeed a lot of different approaches here. I think our experience is that a digital twin is not one twin, it's actually normally a twin of twins, what we in the Cognitwin project have called hybrid twins. But in general, depending on your perspective, there will be different twins that need to be related, which I think we all appreciate. We heard also this from David now about the functional and the product and the process and different perspectives. And of course, each of those will have individual models that needs to be related. So I think what we need in general is a framework which allows different models to be managed over time and related in time and in space and other dimensions. And with that, it will be possible perhaps to relate more of these different approaches to each other under a more common framework. Because as you see, Different domains have their different perspectives and approaches and history. How can we benefit from this, particularly when it comes to cross-domain situations, which happens more and more in complex scenarios, and what can we learn from each other? So we will not resolve that here, but I think we will try to initiate some processes on looking at similarities and differences, and how maybe these frameworks can evolve in such a way that they can relate to each other and be interoperable with each other, and maybe grow somewhat in same directions to have further synergies in the future. But I would like to hear comments from the presenters on this, on your views on where you think the effort and focus should be, and what benefit or opportunities you see from synergies, or if you think it's best to focus on the core approaches that has been presented now without relating too much to others. Maybe going through the presenters in the way that they have presented, starting with Nenad and then following the sequence. So Nenad, what is your perspective on this?
I already raised the hand, so I anticipate. Thanks. Look, there is a big issue in how we are validating the value of the twins. I will go to an example I already presented in my presentation. It's about the steel industry. We have a ladle which should be used n times, and is usually around 80. There is an operator who is deciding should we go to the next or not to the next one hit. The cost of the ladle is extreme, so like I would say hundreds of thousands. The cost of one hit is like 2,000–3,000. We are building a system, a digital twin system, which should support in deciding how many hits can be done more. What does it mean? It means that we are saving 2–3,000, okay, euros. I'm just estimating, so don't put me wrong. And we are building a system, and we are building a hybrid, and then a cognitive twin. So we are putting really machinery in order to do something which is saving 2–3,000. But if we fail, then it is like failing. It means that we say, the system says, okay, look, you have to go, you could go to the next hit, and then the wall will be broken, and then we have the cost of 200,000 of euros. So this is really interesting because obviously the adoption is depending also on this. And the guy in Sydney, I'm quite transparent here. Okay, they're saying, look, Nenad, everything is good, but you know, I have to be on the safe side. I have to really look into what is the cost, what if. So I think that we really should invest in the methods how we are validating all this, all the cost benefits of the digital twins, because the technology is technology. Okay, we can do everything. We can simulate. We can do whatever we want. There is a price. There is a cost. But also there is a kind of benefit. There is a kind of the risk. And I think that nowadays, because digital twins are hype, is completely missing. And we are building the twins, and we say twins are good and cool and standards and so on. But then on the adoption side, we have manufacturing SMEs which are really not understanding the thing. And they have the big industry which can understand everything, but is really, I would say, reserved regarding the cost. I'm optimistic, okay? I'm not negative. I'm optimistic. I'm just saying there is a kind of homework on our side as a technology provider, really to give them the arguments and the analysis, and before building the twins, to do the cost benefit analysis and things like this. So once again, I'm positive, but there is a homework. Thanks.
Thank you, Nenad. Moving over to Georgios and the new project on digital twin of the ocean. How do you view this?
Yes, I think the environmental digital twins are different than the ones that I saw in this presentation session. I think that in the environmental digital twins, we try really to understand how the ocean, in our case, or the Earth operates, and how we are able to simulate and forecast the future. We need a lot of sensors for this. We need really to invest highly and heavily on sensors. And this is why in Iliad we try to integrate low-cost systems in our approach. This is because we have satellites to measure the ocean on the land, but they only measure the surface of the ocean. They cannot give us any information about what happens a meter below the surface. So in order to be able really to understand how the environment operates, we need a lot of to invest heavily on this. And then we have to run a series of downscaled models, because for the moment we have a lot of models simulating the atmosphere and simulating the ocean, but very coarse models. Then in order to be able to develop this DTO, we need to downscale and go down to very fine resolution to be able to provide this information to the various users. So from my perspective, again, the cost is related to these two issues. One is the monitoring, and the second is the modeling, because we create a lot of data out of these models, and we need to be able to sustain the systems and in order to develop decisions.
Thank you, Georges. I think a cheaper sensor is also a common theme among these different domains. But let's go quickly through, since we're approaching the end of our time slot. For the building and construction sector, Gabor, what is your perspective?
Yeah, I think it's at least for the construction part, we have already a synergy with the manufacturing. So at least the IFCs, they have a background very well established already in the computer-aided design. So there is a natural synergy between the digital twin for manufacturing and the digital twin that is being developed for the construction sector itself. But in addition to that, I think the twin itself, it will not help, as I think you have already asked this. We need workflows, and it is also what we kind of try to focus on, that we need the workflow related to work with digital twin. So in itself, it is just a software tool in this sense, and it will not help the SMEs, it will not help the construction sector to come to actually to the new digitalization era. We need to teach and provide actual competence for the construction companies to use the digital twin in the form that it gives additional value to them. So I think in itself, and also whatever we presented here, it is an extremely powerful tool, but the sectors, and especially construction sector, who is not really matured enough in order to use these tools, they need an additional push in form of digitalization.
Thank you, Gabor. From the Factlog project, Kostas? Do we have Kostas here? Did you drop out? Maybe. Well, we'll come back. But let's jump to Stefano and the Cogniplant project.
Yeah, well, I think that we have highlighted a number of challenges, and I think that the multidisciplinarity is definitely one of the ones, possibly the most challenging one, the greatest one. In fact, we have very different sectors that could benefit from digital twins, but it's not really straightforward to find the synergies and to deploy them, to actually benefit from them. I think that in this sense, standardization plays a crucial role, even though, I mean, in some cases, I think that really the challenge is possibly out of scope, because the field of application are too different to really benefit from some sort of cross-sectorial, let's say, activities. I think that one very interesting point concerning sensors happened also in Cogniplant, because we are struggling with one of the plants that is somehow missing the possibility to monitor in real time the heating value of the fuel that they are using for their production, which is like one of the pillars to get an increase of efficiency of their process. And unfortunately, this is one of the cases where you are really exploiting beautiful data analysis, data mining, and cognitive technologies, but somehow you are lacking like the entry point that is data generation to benefit from this. And unfortunately, sometimes technical limitations occur, and we have to keep them into account also in the planning of the project. But of course, what is good is that the technologies that are at the base of the project can be beneficial, even though there are these limitations related to the sensors part.
Thank you, Stefano. Then from SIRIUS, David.
Yes, I'd just like to emphasize the point that we can do all the digital twins we want, but if you don't have good sensors or good measurements or enough measurements to do it, you're going to be guessing and in trouble. But yeah, one last comment about asset administration shell, which I think was what we're talking about. My reading of the asset administration shell is that it's a very good tool for exchanging information about specific pieces of equipment between vendors and operators, and giving that sort of support to that sort of chain once you've got your equipment. One thing which can be done with very low-hanging fruits is to actually take the type of information from the various disciplines and creating a set of standard asset administration shells so that you can agree on how you send your specifications and how you get the specifications to back, and then you can unpack that data back up into your digital twin.
Thank you, David. So that will be some input, I think, to further discussions. So indeed, we'll continue this discussion in the future in different cross-domain discussions. Of course, each domain will also evolve. So I think we will have a context now in BDVA and in ADRA and all of these projects for further collaborations and synergies. So it will be an interesting coming year, I think, exploring that. Now our time is up and it's Friday, so I think you're free to take a weekend. Thanks for joining us and supporting EBDVF and BDVA. Looking forward to further discussions with all of you, and thank you to all of your presenters for good contributions. Thank you, and have a nice weekend.
Nice weekend, ciao.
Thank you.
Thank you.
Thank you.
Goodbye.
Bye-bye.
Have a good weekend.
Yeah.